Start here, we're going to do a land recognition.
At least the summer.
So land switch.
I can take one, but I may have to transfer money. I don't have cash. That's fine? Okay, you will. Okay. Then maybe you can send me the email or where I this one. Yeah. Okay.
I can't get
We dedicate ourselves to move forward with partnership for Indigenous communities in a spirit of reconciliation and collaboration. So good evening, everyone, and welcome to the RASC Winnipeg Center monthly meeting, public meeting. And our theater session is going to start off right away here, and I'm going to introduce Dan Rench, who's also on the council, and he's going to talk tonight a little bit about the Explore the University program. Please welcome Dan Rench.
Welcome. So you're interested in astronomy, huh? What happened? Your loved one gave you a scope for Christmas? Maybe you're out at the lake and you're out one night and you say, wow, that's a beautiful sky. I can't see this from the city. I'd like to learn more. Or who knows, maybe the latest space program, all the rockets going up, some massive rockets, everybody's getting prepared to go to Mars. Maybe that has come on board. Or maybe you're retired and you said, you know what, I've always wanted to do this, but I've always been too busy with work, so now I'll have time. And you see, I put the little smiley face there, because anybody who's retired realizes you're busy, as busy, or more busier now that you're retired. So now what do you do? Well, you kind of find out about the RASC, and you come aboard us, and you join us as a group, and this Explore the Universe actually is something for beyond people of the members of the RASC. You come and join us here, and you're going, I wonder what they can do to help me learn astronomy. So when you take a look at, I just wondered why there's no at the top. That's because of me. When you take a look into the Observer's Handbook, that's the booklet that's given to everybody once a year, you'll find out that there's 8 observing programs. So the RASC, over the years, has basically structured itself to give you the opportunity to learn to observe and proceed as you go along. So there are basically 2 of them for first-time stargazers, Explore the Universe, which I'm going to talk about today. And then there's a secondary one, if you're interested in the moon, called Explore the Moon. They're both very basic programs, and the intent is to get you started. And then, once you get going with your observing, you'll probably find yourself, well, I've got goals to get even better, and you'll find out that there's 6 other programs, that 6 more challenging ones. The next 4, and a whole bunch of members here have their message catalog and find us at ABC. There's the Lunar Observing Program, the Double Stars Program, and then finally, when you get really good at observing, there's 2 challenging ones. And I know when the RASC says they're challenging, you have to have a large scope and good eyes and know your ability to find your way around the sky. So this is, what I'm referring to is the first of the start of your journey through astronomy. So it really is aimed at the novice. So the intent is to get you observing the sky. Maybe you've been an armchair observer and you're thinking, well, I really should know a little bit more about the sky, so they'll get you out there. The other intent is to get you started to do things in a better way, in a way that you can progress, learning good habits. The whole program itself is arranged so that you can learn a little bit about a lot of different things. So it's wide-reaching. It's not just one specific like the Moon program. The Moon program is. We'll touch on a couple other things that I will mention as we go along. And then finally, it's to encourage you to get out and do observing. And then if you are doing observing, I know there's a lot of members here who actually enjoy the public events that we have. So once you get started and you feel comfortable, you finish this program, you'll feel comfortable enough that you can come and join us when we have our public observing nights. When we get together with others, we can pass along your knowledge. So what do you need to start? Well, the program is designed to be able to just use your naked eye or binoculars, and that's the two things that they specify. They say that you can use a telescope if you want, but when you're doing these objects and finding these objects, you're not supposed to be using the go-to feature. And like I said earlier, it's a choice of objects, and the objects are selected for the whole period throughout the year. So it's something that you can start at any time, and that you can probably complete within a year. I was going to just mention about the part that I've got a little star up there, because I think that this program, if you have a telescope, and even if it's a department store type telescope, one of the ones that's not really fully capable, it's something that you probably want to use with this program. This was the thing that when I started up doing research on it, this is what really kind of got me going, is that of all the programs that we have for observing, this one's probably the best supported. And by that, there's the most things associated with it, most resources on the RASC list to do this program. And this is just an example off the page. It starts with an actual video that tells you about this program. It's a short video, does not provide the detailed and quantifiable, excellent material that I'm going to provide you, but it is a short thing to do that. And then when you go on the RASC, you'll find other things. And an example is using the star finder. We've been passing these out to people who have been coming to our meetings, coming to public sessions. So there's even videos about that. They even went as far as to produce a guidebook. Now this whole program and going through this is a little bit paper intensive. So you can copy off documents off the website, and I'll show you that in a moment. But the key here is that they actually produced a handbook. Some people, that would be something that they invent from, and this is a booklet that you can use to not only record the objects that you've seen, but also has the paperwork associated with applying for your certificate. So what's the catch? This sounds too good. A really well documented and supported program. Well, there's going to be some late nights. So part and parcel of doing the observing and trying to catch objects in the summertime is you have to stay up past 10 o'clock. It's a challenge for some people, but you'll have some late nights. You're going to have to record your observing. So that way, when you say, well, I've seen those objects, some people need to know, and you'll need to record them. You'll need to sketch some things, and I'll get into this a little bit more, because the sketching, your drawings will help us verify that you've actually seen the object. At the end of it, you'll have to fill in a report card sort of deal that says all the items that you observed. And then when you do that, you'll be applying to get not only a certificate, but also a pin. Now, I know Gail has a pin, so I asked her to bring it along, so during the break, you can all come over and see what the pin looks like. How many pins do you have there? 3. She looks like a general, military. And to do the recording and the sketching and the logging of this, you're going to have to do it at a quality level. Because you've got to please the Center's Explore the Universe coordinator. And that's me. And I will be picky. I will ask that it's, you do some good work here. So do you need anything else? Well, you could probably use a planisphere, because that will help tell you, what constellations are and when. So, it's a program for the whole year, so it helps you arrange what objects you think that you may want to be seeing at any one time. It is a binocular program for some of the objects, and when you're using binoculars, you want to have them steady if you're doing real observing. So I showed you the little binocular adapter that you probably want to try to find one of those. Most binoculars have the ability to mount them on this little bracket, and that mounts on a tripod. So that means when you start looking at something, say the moon, and you're trying to see something, it's not sort of moving around. You probably want some booklets. I show a couple here. The book Night Watch is really good in the fact that it has some easy star charts in it that you can flip through and you can use them when you start hunting for some of these objects. And then you'll be out there and you'll be wanting to see but not wrecking your vision with bright lights, so you're going to need a red flashlight. And everybody else around you will be pleased that you have a red flashlight. So this is a program aimed as an individual. You do it by yourself. You'll have to find the objects in yourself. You have to record them yourself. Write up what you think of them by yourself. The second part of this I wanted to show is the Print at Home Explore the Universe workbook. So there is pages that you can print out, a workbook that will help you basically go through and help you document what objects you've seen. And then as I said earlier, that once you've got your workbook done, you come to me, and through the local center here, we will get you your certificate and your pin. Now, if you happen to be somebody who's joining our program by, is it on YouTube? Yes. And if you're not a member of the RASC, this is one of the certificates that is open to you. So you can still not be a member, but you can still apply for this. And this is off the website, and these are some of the documents that you can get. So you can get an English or a French version of the Explore the Universe guideline. It's about 8 pages telling you what objects are included in it. I'll touch on that as we go through. If you want your own workbook, as I was describing earlier, it has that. It's something you can print off. 2.4 meg, I think it's about 48 pages long if you want that. Interesting enough, there's logbook pages, so that if you want to do more than the basic number of objects you have, you can print off additional pages. And there's a left-hand version and a right-hand version. So it depends upon how you sketch. I thought that was kind of cool. There is a variable stars expanded supplement to this if you decide, and then the actual fillable application form. So what's in this program? Well, it starts with constellations and bright stars, the moon, the solar system, deep sky objects, and double stars. Now, it has here that the fact that, for example, with the constellations and bright stars, 12 are required, 24 will be identified as ones to go for, 12 are required. And I myself thought you might be more wanting to do all 24. I mean, you want to start it off and do all the constellations and stop at 12, or you want to make sure you get all the constellations for the whole year. So although this says, the minimum requirement is 55, 12 of that particular object, that may be an area that you'd want to do all 24. When you get into the moon, it gets more challenging and some of the stuff. The solar system is 5, but maybe there's some other objects. If you have a telescope, you'll probably want to do more objects, and I'll show you that in just a moment. So here's an example of what's in the guideline book. So here's for the winter. You could start this already and just go online and get these pages. And there's the list of constellations that you'd be looking for, and a list of the bright stars that you'd be looking for associated with it. So when you go through the initial guideline book, you'll see these, and you'll check off the ones that you want to see. And I added this point at the bottom. So when you tell people you're an astronomer and you're outside with them and you're looking at the sky, do you notice that they're kind of like, well, what do you see? What do you know? So one of the nicest things about doing the constellations, and why I suggest to do them all, is that with the constellations, it's nice when you go out in the winter time and somebody says, whoa, what's that? And you say, oh, that's Orion. And do you see the bright star over there, Sirius? Yeah, that's with Canis Major. So this is the first area, and probably as you get started in working in your handbook, this is where you start. This is where you find the constellation naked eye, you find the bright stars, and you can already start documenting what you've seen. Next comes the moon, the moon, and there's a couple of sections to it. The first part is the phases, and this is the easiest part of all. There's 8 different time frames that they tell you to observe, and this is all visual, and it's the phases of the moon. So get a young crescent, get it when it's quarter, get it between quarter and full moon and past. And this is one that if you're trying to get the waning crescent on the other side, you're not a morning person like me, then maybe it's one of the objects that you don't get. But it's a good way to get started seeing the moon in different phases. The next part's a little bit more challenging, and as you notice, it shows in the chart here, where it says VBT, Visual Binocular Telescope. So this one is suggesting that you pretty well need binoculars for this. And again, like I said, set them up in a tripod, take a look, have a map of the moon with you, and start looking for some of the largest for example, tranquility. These are fairly large objects, so these are relatively easy to do. You're looking at the phases, then you're looking for things on the moon that are very large, then you're going to be looking at things that are very small. So do you see how you're developing, you're observing? So this is something you could start doing some of the things and work your way up. Impact craters. And there's several, as listed here, many impact craters that are fairly large. Here you see they say binocular or telescope, and this is what I was saying, even if you have a smaller, rickety telescope, the moon is still a very good object to see it with. And these are some of the major large craters worth seeing. Then we get into the solar system. This is not too bad. It's seeing at least 5 of the 10 objects. And this is not the full list because it includes Neptune and Uranus. I just didn't have enough room on the page. But this is an easy thing to do. Put down the date, when you saw it. You'll have to know that it's up in the sky because not every object is visible all the time. And record you're seeing all these objects. And often there's conjunctions, and that would be even more fun because the diagram can say, well, there's Venus beside Saturn. I saw it, and it was 2 degrees apart on that particular date. So that makes kind of fun with this. The last thing that you'll probably want to do is after you become quite comfortable with the equipment that you're using, be it the telescope or binoculars, then comes the deep sky objects. And although some of these are large objects and are pretty good in binoculars, you may want to have some of the higher power binoculars. Like the club has a 15 by 70s as a loaner set of binoculars, so you loan up one of the larger sets of borrow the larger set of binoculars from the club and look at some of these objects with that. So this is where the challenge is. This is where it becomes a little bit more difficult, but if you've been doing all the other things, by now you're feeling comfortable and you're starting to be able to find things. And then you get into other deep sky objects, and they're not difficult objects. The Pleiades, for example. Naked eye, you can see many of the stars. With binoculars, it's a beautiful object, Orion Nebula. So things that are fairly major, easy to see. The catch is you'll have to record it and prove it to me that you've seen it. There is a section on double and multiple stars, and I know Gail loves showing double stars when we do observing nights. A lot of people really appreciate this part when you're looking at a pair of stars that are associated with each other, and there's distinctly different colors. So it's just an interesting area to be observing. Here again, you're using the first object. There's a magnitude 6 and 6.2. So here again, you're going to need binoculars for sure with this, and then you may want to use a small telescope with it. So what is an observation? It's basically a brief description of what you see. So you've gone out, you've set up, you've seen it, now what do you do? Well, you want to record what you've done. And you'll see on the pages, you'll record when you saw it, the date, what the weather was like, whether the moon was out. But here's an opportunity for you to start your developing of a process of recording your observations. For prosperity, for you to look at when you get to be my age and say, wow, look at all the things I saw when I was younger. And this will also, in doing this, in logging and writing descriptions of this, will help you improve your observing. On the RASC website, there's sections of observing tips and expectations. So that's something that you should actually go to at the beginning, because then you'll start to understand what it is that you'll be looking for to some degree. I'll talk a little bit more about what I'd like to do with the people who are thinking of doing this particular program. Maybe we can do something where we get together and we start talking about some of these items and give you a little bit more of a push start to get going. Do you have to record them? Yes. But recording will benefit you. And I don't know if anybody's ever talked about or heard Scott Young when he talks about observing, but when he was younger, we taught him to observe, and he really appreciated getting the lesson early, because he says it really helped his observing skills. It says here that the logbook, you can do an electronic version of it, but I think the majority of people probably land up doing it on paper. And there's also, and I didn't highlight it on here, but there's also another website link that they have about the observer's logbook. So it's somebody who developed specific pages for some of the other programs, but they talk about what it is and what to put into it. So it's a little bit of a quiz here now. So you see these two objects, and maybe one of them was, or both of them were one that you have to look for. So how would you describe it? And is there any of the skilled observers who'd like to describe what they see when they're either one of these? Like, how would you describe the one on the left? Open cluster, a whole bunch of very bright stars.
Surrounded by haze.
Surrounded by haze. That's probably more than that. But, that's how you'd start saying, well, it looks like there's about a dozen bright stars of brighter magnitude, and then there's probably another couple dozen that are a little bit fainter than that. It's not a lot of stars in this particular object. And then you take a look at this, the second one, and you say, well, how do you describe that? Well, it's a globular cluster, very bright at the center. But you can resolve stars in it. There are a series of bright stars around it. And when you do your drawing of this particular object, you're looking at it, you say, well, the two stars on the left, the one on the right, the bright one, the one at the bottom, well, I'm going to start drawing by showing those stars, and then show the placement of that object within those stars. Then I take a look at your logbook, and I go, oh yeah, I can see these stars, showing exactly where the object is. So that's part and parcel of this process of documenting and drawing the objects. This is the form that they have with the workbook. Mine has, the ones I have, has 2 objects per page. So it gives more room for you to put down a description of the object. When I was describing the other object, the previous pictures before that, when you have to start writing about what you see, you have to start thinking, well, what am I going to put down there? You really actually start looking at what you're seeing. And this is the whole intent of this. This is why sketching is so good. Because once you get started, you start saying, oh, I see that. Oh, I see that. This is one of the other forms that you require. This is the final form that you're putting down, which phases of the moon you've seen, etc. 4 of 8. Some of these I think you may duplicate, because you may want to see all 8 phases of the moon. So once again, the observing tips and expectations page. I'll touch a little bit about sketching. These are sketches, these aren't photographs, but they look pretty good. So as I've written here, there is a big difference between just a quick look and an accurate sketch of what you see. So for example, the galaxy on the right side, how do you sketch it? Well, you've got to make sure that, because it's an edge on, it's really edge on, you've got to show that there's a ratio of how tall it is or how small it is height-wise compared to how long it is. So in sketching, you'll want to say, well, that's what? 8? 10 times as wide as it is tall? So now, you're trying to get that in your mind exactly how you draw it, and that's what you come up with, is that you'll see the details start saying, oh, wait a minute, okay. And how far does the bright portion of the center of that galaxy go? How much is brighter? And then when does it really start to fade? And does it come to a nice point at the end? Or does it, in this one, the case, on the right side, it kind of starts to spread out a little bit. So it looks like it's a little bit of a warp. Yeah, this is the type of stuff that you'll be writing. And there's just some more sketches. At some point in time, we'll probably get Sylvia to talk again at some point in time more about sketching. She's the one who drives the sketching part of our club. So basically, the whole intent of the program is to start with good habits. Doing the logbook, doing the writing will help you develop your observing skills quickly. A couple other things, you'll learn things such as averted vision, where you're not really looking at the object, you're just kind of looking off the side where the more sensitive part of your eye is receiving the photons. So it shows you fainter objects. You'll work on making sure things are in focus and they're not fuzzy. So this program is made for both members of the RSC and people who aren't members of the RSC. You can both apply, get the paperwork together, and get it to me, submit the submission to me. Anybody who's online and seeing it, and maybe out in the country, they can contact us through our website and direct it towards us. You can't buy your way into astronomy. It does take some time and effort. So you try to go outside when you can, and that's what this program will do. We'll drag you out all through the whole season, all 4 seasons of the year, and we'll challenge you by looking at different objects. And there are a whole bunch of useful sites on the RASC website that I've just listed here. So that's the conclusion of the talk. I just wanted to add that if there's anybody in this room who wants to be part of basically some information session, we can get together on an occasion. We can talk about equipment, kind of getting you started with some of the basic fundamentals of the equipment that you're using, and we can talk a little bit about the worksheets and what objects to choose. So I'm thinking we'll probably do something in the March time frame. See me at the break of the meeting.
Thank you very much, Dan.
I wanted to add one more thing. I see Brian is here. So he's going to be going over what's up and he will describe which planets are visible at this time of the year. So if you pay attention to him, that's the planetary part.
All right. Thank you again, Stan. And we're going to now move into some more of the meeting. So tonight's meeting, basically, we just did the beginner session there with Stan Runch. Shortly, I'll tell you the meeting welcome, do announcements, and what's up, what's new, a break, and then our main presentation from Alan Dyer. So announcements. Lunar Scope Coordinator Mike Krakus. Mike, where are you? I saw you. So anybody who doesn't know who Mike is, he's the person you would see at break if you wanted to talk about getting one of the lunar scopes. And as Stan mentioned, there are a set of binoculars available. First Fridays at the Manitoba Museum, contact Scott. He'll put out a notice when we're able to go and have volunteers there. That's part of our public outreach and working with like-minded organizations. Following on that, we do have calendars for sale. Abdul has told me we're having a fire sale tonight. Abdul just held his hand up there. So $15 per calendar, not $18, $15. We got a deal tonight. And if you happen to be out there online and you want one, send it in chat and we'll make arrangements to get it to you. Oak Marsh is another one of our outreach programs and working with like-minded organizations, and that's the third Thursday of every month. And usually there's an advertisement. For anybody who is not, for RASC members who bring a scope, which is set up at the up on top of the observing area, there's no admission to go there for that function. So you're all welcome, but you need to bring a scope to be able to assist with the public outreach afterwards. So, big pile of books up here. So, at break, it's not a free-for-all exactly. The idea is what we're going to do is we'll start with members who have been here for 1 year or less, or sorry, 3 years or less. Let them have a chance to come down, root through the boxes, and then we'll open it up to the rest. And we're going to ask just initially you take one book, so everybody gets a chance to pick it up. And this is on behalf of Jay Anderson there, sitting there thumbing through one of the books. And we thank Jay for bringing the books in.
He doesn't want to go home with any books.
He doesn't want to go home with any books, and I said, I guess he's not going home. Unless we all help him out, of course. Spring tune-up. So this has been scheduled. More information will come out, basically March 25th. We have 1 to 4 at Eastview Community Church, and Darren Henning and several other volunteers are offering to bring in your scopes. They'll help you tune them up, give you some pointers on cleaning the lenses and things like that if you need that. So this is a service open to all the members, and there'll be more information published on the groups.io as we get closer and the details are firmed up. Science Rendezvous, which is a program, again, working with like-minded organizations that the University of Manitoba hosts every year. We've been invited to participate, and we are going to participate. We are looking for volunteers, and if you're interested in volunteering, yeah, Stan's looking. Is that really my name up there, volunteering? But yeah, Stan Runch, Stan was just up here, and he's sitting over there at break. You can track him down. If you're interested in helping with that or volunteering, please come over and see Stan. Lockhart Planetarium is now open again, and that's the U of M's planetarium. And again, working with like-minded organizations, getting the word out. I believe their first night's February 22nd. Is that correct?
Yeah, that's correct.
There we go. And what time, sorry?
7 p.m.
7 p.m. I forgot to put the time in. So it's great to see that that's open to the public again, and events are running again. The RASC store again, the link is there. I'm going to change the color. No, not really. We'll get the color change. But again, if you wanted to buy the RASC Winnipeg Center mugs or T-shirts or things like that, that's available there. You can get just log on and buy one. You don't have to buy 100 of them. You can just buy one and make it for you to send it to you. And several members of the club have used it, and it's a good product for a reasonable price when you're buying 1 or 2 of it. So with that, we'll move on. Members observing night, you'll see when Brian talks about what's up. Whether or not it looks good, I know when I looked at mine, it said it was foggy tomorrow night. So we'll see. Kind of hard to observe in the fog. Good for planets, yeah, that's about it. But, I mean, just to build on that, if you're like thinking about the Explore the Universe, you still go out and look for the planet, because you can still observe the planet. So that's a good thing. I'm just going to quickly check the chat. We're okay? There we go. All right, so the next one. There we go. So I'd like to introduce our next speaker, and it's What's Up, and Brian Sapp. Please welcome Brian.
All right, I don't know, can I take my mask off? Okay. I just feel a little more comfortable without it. Okay, so hopefully I'm going to be shot this time. Okay, that's... There we are, and that concludes for What's Up for February.
It's going to be cloudy anyway.
Is it? Okay, thank you. All right, okay, so let's, I'm Brian, we'll talk about a little bit what's up for February 2023. Some interesting things are happening. And can I do this? Okay, we'll talk a little bit about planets, and Stan did mention about what planets could be visible. Unfortunately, only one planet is going to be really visible, would be Mars. That will be visible throughout the whole night. We're receding from Mars, so we're moving away from Mars because we had the opposition back in December. As I have it here, Mercury will be only visible during the day, Venus partly in the evening, as well as Jupiter. Jupiter will be visible during part of the evening, early twilight kind of thing. Saturn will be too close to the Sun to be viewed. There will be conjunctions on February the 16th. So I'm sorry, only one planet is going to be really visible, maybe Jupiter in the early evening. That's about it. Okay, so what events do we have that's coming up? It doesn't look like much, but I'll get into greater detail about it. We have the zodiacal lights that are coming up on February the 7th. That's for the next 2 weeks, but this is in the evening, not in the morning. So it's going to make it, if you do want to try it, especially tomorrow night, at the members' night, if it's clear enough, and we should be relatively in a good place to have observe it. You will see a cone shape. I don't have a picture of it. Usually I have it, but maybe next time I will. But it's a really interesting thing to have a look at. When I was out with some friends back in Arizona, Jay showed me, it took me a while to figure out it's bigger than you expected. So anyways, of course, Saturday conjunctions with the Sun on February the 16th. We have the new moon on the 20th. The first quarter is on February the 27th. And of course, Mars is 1.1 degrees south of the moon on February the 28th. I had to check a couple models on this because I thought it would be the evening, but it's the morning of the 28th. But of course, I'll get into a little more details. All right, so I have here for tomorrow night, everything goes good. We do have the comet. I did try to take a picture. Again, I'll talk a little bit more about it later and show you the results I get. It was pretty cold that night. Minus 29. Okay, of course, like I mentioned, we have Mars up here. Anyways, we have Mars. And right next to Mars, we have the comet. So it should be a relatively easy thing to have a look at it. If you do have a pair of binoculars, you would have a good chance of probably seeing it. The magnitude is only 7, but we'll see how it goes with the sky conditions. Of course, Orion, constellation Orion with M42. You never look the constellation. It's going to be quite easy to see it. It's going to set earlier every time throughout the year. The Orion constellation is probably one of the better things, especially if you're new to astronomy. M42 is one of the easier objects to observe, especially if you have binoculars, if you have, or a telescope. There's an easy target. We do have a members night tomorrow, of course, there will be people to help you out. Okay, oh, this is close up. I thought I deleted that. Okay. Anyways, I'll move on. Okay, as I mentioned before, Jupiter, we do have Venus. Venus is not really, you can't really observe Venus during the evening, even in the twilight, because it's just, the atmospheric conditions is way too hectic. You have to see it during the day. But there's precautions you have to take, because during the day, when you look at Venus, it just looks like the basis of the moon. But we do have Jupiter in the early evening. This is kind of nice. And right here, I do have the crescent moon. So this is on February the 22nd. So there'll be a nice opportunity to get the crescent moon. It'll be in the evening when it gets dark enough, so that'll be interesting to see. Here again, this is the February 27th. We still have Jupiter and Venus there. And of course, we still have a little bit of the crescent moon there to have a look at it, but it's more in the twilight. Next, this is what I kind of mentioned about earlier. It was kind of hard, because I thought it would be the evening of February the 28th. But it turns out to be the morning of, as you can see here, it's 1 o'clock in the morning when the conjunction is going to happen was 1.1 degrees south of the moon. But throughout the whole evening of the 27th, Mars is going to be dancing around the moon. So it'll be a pretty good evening to have. Okay, as I mentioned, we are receding from Mars. Unfortunately, Mars is one of my favorite planets. The little history of Mars, every 2 years we catch up with Mars to have the oppositions for it, get close enough to have it observed. But unfortunately, for every 2 years now, the planet is going to move further away from us in terms of distance. So if I have it here on 2022 here, December, it was 17 arcs across, but the next 2 years, 2025, you're looking at it drops down to 14, and 2 years after that, it drops down to 13. But then after that, it's going to climb back up. So I think it's roughly 2040 where we get back up to 24 arcs per second, or 24 arcs across. And that would be a really spectacular to see, because it's big enough that we want to have a look at it. All right. So, moving on. Okay, as I mentioned, I did try to take a picture of the comet. And that's the best I can do, because my mount froze within 5 minutes. I had my van running, my SUV running for 5 minutes. And so that little green dot there, see flares there, right next we have the Big Dipper. That little circle there, that is the comet. I don't think I can blow it up here, but if you do blow it up and play around with Photoshop, you do get a hint of the tail. But when it's minus 90 degrees and with the wind chill of minus 33, well, you know, I was pushing it in the middle of nowhere, near Stony Mountain. So anyways, let's talk a little bit about the forecast. Well, unfortunately, this is probably the only warm weekend we're going to have according to the model. I do remember Jay's presentation last time about there are certain models. I'm comfortable with this model. Seems to work for me for most of the time. But for temperature-wise, it's going to be a warm weekend. But next weekend, we're going to go back down to minus 25. So as for cloud coverage, maybe tomorrow night, a little iffy there. But definitely we might have some clear nights tomorrow for the observatory night. Hopefully we'll have it. Other than that, there doesn't look very good for the forecast in terms of cloud coverage for the next couple of weeks. I did try to jump around to the 16-day forecast. Again, the red represents the temperature. As you can see here, by February the 24th, we're right back up to minus 25. So anyways, take it as we get it. As terms of cloud coverage there, the bottom line is indicated here. Again, tomorrow around 12 a.m. Friday's good. Saturday, a little iffy there. I heard some forecast can change any time, but this is the model I'm more comfortable with. So hopefully tomorrow night during the members' night we'll have something for you guys there. But that's it. That's all I have for What's Up, February 23rd. Thank you.
very much, Brian. And our next speaker to talk about what's new is Dr. Danielle Hood.
Sorry, everyone. This is my fault. One day I will be on top of things enough to get Judy my talk before the meeting starts. I get very nervous when Stan tells me it gets busy for retirement. Things will not look good for me. I will take this moment to shamelessly plug the open houses at the Lockhart Planetarium. So we had our first one last month, and the next one is February 22nd, so it'll be the last Wednesday of every month at 7 p.m. going forward. It'll be a mix of like a what's new under the dome, and then maybe a research talk. So the last one was kind of a mixed mythologies, mixed culture mythologies, some winter constellations. It was really lovely. I have a group of students that are learning to present, and so they presented to the open house. We had about 25 people show up despite last minute advertising. I have set up an Eventbrite site for ticket management because space is limited. It's 55 seats in the planetarium, and I don't want a situation where there are so many people that turn people away. So the link to the Eventbrite page is on Instagram. It's also on the Lockhart Planetarium website. And you can also find the open houses through the Faculty of Science events page. But it should be a lot of fun. It's Tuesday. That's okay. All right. Okay. Hi, everybody. For those of you who don't know me, my name is Dr. Danielle Hood. I'm an instructor at the University of Manitoba and director of the Lockhart Planetarium. It's my pleasure to be here with you today. I got completely carried away, so there's just one news story today, but it's potentially very exciting. And so the news story today is a Nature paper that was published at the end of January, and it is evidence for lunar tide effects in Earth's plasma sphere. And so this diagram is pixelated. Hopefully they're not all like that. But we've seen tides in Earth's ocean, in Earth's crust, and this is some of the first evidence of seeing tides in a collisionless plasma, which is really exciting. Okay, so just to make sure that we're starting on all the same footing. So lunar tides are tides that are caused by the moon. They're caused by differences in gravitational forces on either side of an extended object. So on Earth, we have tides that are caused by both the moon and the sun, the tides from the moon being stronger. And we get kind of this double tide. So we get two high tides at two different locations on Earth. I'm sorry, these are really pixelated. So if the moon and the sun are aligned in a straight line with the Earth, then we get really high tides, basically right under the moon, and then on the side of the Earth that's opposite from the moon. And then if the sun and the moon are kind of 90 degrees apart, then we get lower tides. But because the moon's gravitational force is stronger, we get a higher tide right underneath the moon. But we have semi-diurnal periods due to Earth's rotation, and then we get semi-monthly periods from the moon's orbit, because it takes about 28 days for the moon to go around the Earth. Okay, I mostly say this because I'm going to be contrasting this with the result that was published recently. Oh, looks like it's going the wrong way. There we go. All right. So we found tides that behave similar to what I just described in Earth's oceans. They've also been, and so they're important because ocean tides influence heat flow from the equator. But lunar tides have also been observed in Earth's crust, and they'll create increased seismic activity and volcanic activity. The tides have been observed in the neutral atmosphere, which has an impact on rainfall. According to the paper, Jay can confirm or deny. And tides have also been observed in the ionosphere, which is the upper layer of the atmosphere that is ionized but still collisional. So we're expecting there to be enough interactions between particles that they're hitting each other and transferring energy and momentum. And this has an impact on radio transmission and low Earth orbit satellites. I forgot the one image I forgot to replace it, sorry. So somewhere beautiful in Italy or Greece, I suppose. But this paper presents the first evidence of a lunar-induced signal in the plasmasphere. All right, so just to make sure that we're all on the same footing in terms of what the plasmasphere is. So I'm going to start with Earth's magnetosphere. Yep.
Just getting it so they can hear all this.
Yeah, sorry about that. Test? Yeah, good. Okay. All right, so just so that we're all on the same footing, we have Earth here, this black and white half-half circle. The sun is off to the left in this diagram. So the day side of the Earth is the white side, and the black side of the Earth here is the night side. The magnetosphere is the magnetic envelope that separates the Earth from the magnetosphere. And so very close to the Earth, we have these closed kind of Mickey Mouse shaped lobes that are filled with cold, dense plasma. And this is the plasmasphere. They envelop also the ring current, which drives a lot of geomagnetic activity during storm time. And then further out, we have kind of a more typical but less dense magnetosphere. And there's a really sharp density transition from the plasmasphere and the ring current out to the magnetosphere, the regular magnetosphere. And then beyond that, we have the magnetosphere and the plasma current sheet and the lobes. And we get kind of this magnetosheath region where we have the interaction between the Earth's magnetic field and the sun's magnetic field. So this, of course, is a three-dimensional object, and so this is just another diagram showing these regions, where here I have the plasma sphere in blue, and so it doesn't cover the poles, so it's kind of donut shaped. It's like a torus that hugs it through the equator of the Earth. So when I talk about the plasma sphere, I'm talking about this cold, dense region that forms a donut around the Earth. All right, so the plasma sphere is filled with plasma. So plasma is the fourth state of matter. It means that the atoms are ionized. So it means that the electrons and the protons are separated and act independently of each other. If the gas is collisional, they might be combined, but in the plasma sphere, they don't. And so they stay independent, and they only interact through their interactions with the magnetic field. So the electrons are free, as are the ions. It's a quasi-neutral plasma, which means that there's about the same number of electrons as there are of protons. So it's electrically neutral as a whole, but the electrons and ions are free to behave independently. So the plasma is filled with this. So the plasma sphere is a quasi-neutral collisionless magnetized plasma region. It extends along magnetic fields from the upper atmosphere, and it fills that torus-shaped region around the Earth. It's a cold plasma, meaning that the ions and electrons have a temperature of 1 to 2 electron volts, which is an energetic measurement for energy and temperature. It's dense by space standards, so 100 to 10,000 particles per cubic centimeter. And its composition is 80% hydrogen, ionized hydrogen, 10 to 20% helium. It's been once ionized, and then 5 to 10% oxygen that's been once ionized, and then a bunch of free electrons. Okay, so why did they look at the plasma sphere for tides? So it's most ideal and representative of a plasma-dominated space as opposed to the rest of the Mercury sphere, because the moon is always on the outside of it. It's pretty dense. It's easy to see because it emits a lot of UV, which is what I forgot to mention here. So it emits a lot of UV, and it's got a really sharp boundary, so you can actually look at the surface and the shape a lot more easily than you can for other parts of the Mercury sphere. So the diagrams that I have here, these are two images of the plasma sphere. So this black circle here is the Earth. You can actually very faintly see the auroral oval. So here we're looking at the plasma sphere of the Earth from above. These are UV emissions, so extreme ultraviolet emissions. And this is taken by the IMAGE spacecraft, which has a really elliptical polar orbit. So this is looking at the plasma sphere from above. This image here is taken from the Chang 3 mission, and it's looking at the plasma sphere and the Earth from the side, from on its way to the moon, so from above the moon. So again, this black circle is the Earth, the plasma sphere is here, and then in both these scenarios, the dashed, or the white line, represents the boundary of the plasma sphere. And I'm just going to gloss over the tail for now. And you can ask me about this if there is. Oh, too many. Okay. All right. So why do we look at the plasma sphere? Why do we look for tides in the plasma sphere? So it's the most ideal representative plasma-dominated place to look for tides. The basic properties of the plasma sphere have been studied extensively, and so it's pretty well understood. There's a huge amount of observational data, and there's also a well-defined surface or boundary. So you can look in the same way that we can tell ocean tides by looking at the level or the surface of the ocean. You can look at tides in the plasma sphere by looking at the boundary of the plasma sphere. It also plays a key role in particle exchange and storage within the magnetosphere. Okay. So plasma pause. So the plasma pause is the boundary. So it's that represented by this white line here. So the plasma pause is the separation between the plasma sphere and the magnetosphere outside of it. And so the plasma pause location reflects the dynamics of the cold plasma. It affects distribution of energetic particles in the inner magnetosphere. It influences the excitation and propagation of electromagnetic waves. If you've ever heard of torus or hissed waves, they're located here. And it can impact the radiation belt and wind current dynamics. Okay, so how did they observe the boundary of the plasma pod? So it wasn't all images like I showed. What they used, for the most part, is 40 years worth of data, most of which came, well, a lot of which came from the Themis spacecraft. Themis is the time history of events and macro-scale interactions during substorms. And so it was a series of 5 spacecraft with highly elliptical orbits that swept out kind of into the tail here. So here the blue lines are the magnetosphere and the red lines are the Themis orbits, and so they kind of sweep out and spread across the tail, but that whole orbit precesses. So sometimes that spread actually is forward or to the side, and so as they orbit over and over, you actually pass through the plasma pods over and over and over again. And so you can accumulate that data to get a location of plasma pods boundaries as a function of time and as a function of lunar phase. And so that's what they've done. So here's an example of Themis data to show you just how abrupt that plasma pod boundary can be. So here I have a spacecraft potential, so this measures the electric environment. And so this is outside the plasma pods, this is inside. So this is spacecraft potential. And then the x-axis here is time, so this is universal time, so it's just time of flight. But the second row of numbers are, as a function of, or as a multiple of RE, is the distance of the spacecraft from the Earth. So this 2.57 means that the spacecraft is 2.5 times the distance from the Earth. And then this second graph down here is the density of the plasma as a function, as the Themis spacecraft orbits around. And so you can see that the plasma pods has this really sharp boundary. You can really tell when you're going in and out. And I'm not a plasma pods expert. I'm sure they've cherry-picked a particularly clean data set. But this really suggests that there's a clean boundary coming in and out of the plasma pods. So they've collated 40 years of data. They have collected, so from Themis, from cluster, from image, all of these spacecraft. And they have 50,778 plasma pods crossings by Themis and other missions. So these data span from November 1977 to December 2015. We know that solar activity has a huge impact on the magnetosphere and on the plasma pods, the location of the plasma pods. And so that plume that you see is often a result of the plasma pods kind of settling down after a lot of solar activity. And so they've improved the data down to try and select only times that were geomagnetically very quiet, so that the effect of the moon would be the strongest. And so the criteria for that was the DST, the disturbance storm time index, to be less than or greater than -50. The larger a negative is, the more active things are. AE is another geomagnetic activity index. It measures the auroral electrojet, and that should be less than 300 nanotesla. And then KP, which is a global geomagnetic activity, should be less than 3. So when you start looking for aurora at around KP 5 or 6 or higher. So hopefully really quiet geomagnetic times. And then they've compiled the database of plasma pod perturbations. With those criteria, only 35,982 remained. And then they categorized these by lunar phase. So when you crossed the magnetopods, where was the moon, and did the position of the moon relative to the spacecraft have an effect? Have an effect on the position? So the answer they found was yes. So what I'm showing here is their result for one, but it's 4 different times. And so it is, so delta LPP, the y-axis here, is the perturbation in the location of the plasma pod. So how far it is, either closer if it's negative or further away if it's positive, than kind of the average plasma pod location. For the lunar phase, So lunar phase 0 is full moon, so that's a magnetic local time of 0, 0, I think. I've got a slide next to kind of keep this all straight. But you can see that for the phase of the moon, magnetic local time is where, maybe I'll show it now. Okay, so here's a diagram that helps. So it helps me. So if this is the sun and this is the earth, magnetic local time 0 is kind of midnight. Magnetic local time 12 is noon, 6 is here, 18 is here. And then lunar position is the face. So I have to stop. Sorry. I'm jiggling my finger on to try and show an arrow, but it's scrolling pages instead. So the lunar phase or lunar position is the location of the moon in magnetic local time. So it'd be 0 at full moon. So the moon is, so in that very top graph, the moon is at magnetic local time 0 when at lunar phase 0 full moon. But you can see that the preservation of the magnetopause, or sorry, the plasmopause is 6 or 8 hours ahead of it. And then as we move to the third quarter moon, the location of the moon is at magnetic local time 6, and the bulge is closer to 12. So again, 6 hours ahead. So you could do that again for lunar phase 12. So new moon. This one I don't find so convincing. They're like, the peak is here. I'm not convinced by that one. But again, for the first quarter moon, the moon is at 18, and the peak of the distribution is about 23, so about 5 hours ahead. Okay, so hopefully this helps kind of keep everything organized. This would have been helpful. This is the only slide I should have shown, in hindsight. But the result here is that there tends to be a bulge. There's only one bulge, and it tends to be about 6 hours ahead of the position of the moon. So here, instead of breaking up the data into lunar phase kind of coarsely, they've broken the data up into lunar phase in 2-hour bins. And they have magnetic local time. So if we look at this top left grid, they have magnetic local time on the y-axis and lunar position on the x-axis. And both of them go from 0 to 24. And it looks mostly like a jumbled mess of red and blue, but you can kind of see a diagonal blue line going from the center up, and then above that, less clear, there's kind of an overall red line there. If you take the Fourier transform of that, which shows peaks in periodicities, that's what's shown on the top right, and there are two very, very strong peaks. The data here on the bottom right shows these diagonal lines more clearly, but they've been for lunar phase in larger bins, so it's just a little bit more coarse data. And then this bottom right graph is the change in position of lunar phase, so the size of the bulge per lunar phase. Okay, so schematically, what this means is that we do have a tide in the plasmasphere. The bulge, or high tide, seems to be about 6 hours ahead of where the moon is. So if the moon is at third quarter or local lunar time 12, the bulge of the high tide would be at 18. But there's only one bulge, as opposed to bulges in ocean tides or atmospheric tides. So it shows a monthly periodicity and a diurnal periodicity. The high tide bulge is about 6 hours and 90 degrees ahead of the lunar position. But the signal seems to be pretty strong. So another thing that happens about once a month is the sun's rotation. And so we do know that there's a strong driving of the magnetosphere due to the sun's rotation, in particular, due to co-rotating interaction regions. The authors are arguing that the fact that they selected really low geomagnetic activity would kind of put that effect aside. I'm not certain, but it's exciting to think that it might. And then when it comes to mechanism, how would the moon's gravitational force interact with these particles that aren't really colliding with each other to create a pressure to move them around? The current leading theory is that there's a co-rotation electric field that has a radial component that's anti-correlated with the bulge or the location of the tide. And so that may have something to do with it, but the exact mechanism wasn't proposed in the paper. So the implications are pretty large for our understanding of the moon's effect on our plasma cloud, on the plasmasphere, and potentially on the magnetosphere. And it's fun to think about potential interactions for other worlds and exoplanets. Okay, that's all I got. Thanks. Yeah.
So you said that the plasmasphere time hours ahead of.
Yeah.
Is it possible it's 15 hours behind?
Ooh. Okay, so the question, in case people didn't hear it, so I said that the tide bulge is 6 hours ahead of. Judy asked, is it possible if it's 18 hours behind? Yes, I suppose. Yeah. I'm not sure. I don't know how you would distinguish between the two.
Yeah, I don't know.
Yeah. Yeah.
You said there's a very clear boundary between the plasmasphere and the magnetosphere.
Yeah.
Why?
Oh, that's a good question. Okay, so why is the boundary between the plasmasphere and the magnetosphere so clear? So part of the reason does have to do with this co-rotation electric field. So the magnetic fields are in the Earth are like tied to the ionosphere. They're kind of anchored. But as the Earth rotates, these field lines that are further and further away have to rotate really, really fast. And so there's a point where it's hard to get enough energy and momentum transferred to that point. And so there's kind of a shearing. And the other reason is that these field lines that are kind of open are more likely to interact with the solar wind. And so they don't get dragged around with the co-rotation of the Earth quite as much. Yeah. Yeah, Michelle. Here? Oh. Okay. Yeah, okay. So these things that are sticking out, the like little speech bubble points, those are called plasmasphere plumes. If I remember correctly, during times of geomagnetic activity, the plasmasphere will puff up. Do you know? Okay, I take it back. When the Earth is slammed with a CME or a coronal mass ejection or co-rotating interaction, the entire magnetosphere shrinks down. So the field lines that are on the plasma clouds get compressed, and I think some of the plasma gets left behind, and so then you get this overdensity of plasma that's partially co-rotating, but is now being subject to other forces, and so it kind of creates this plume, and it leaches out into the negative pos. Michelle, again.
I have a question. The tide bulges in the ocean into the moon, is there a lead or lag on that too?
Oh, the lead or lag on the ocean tides? I think yes, but I don't remember by how much.
Because I'm trying to make an analog
So we're going to take a 15-minute break, and what we'll do is, who in the audience has been a member? How's that? We'll start up again at 8:30. But who in the audience has been here, or has been a member less than 3 years? 3 years or less. So those people can come down and get first ticket to books. So come on down if you want to, you're welcome to take a book. And then what we'll do is we'll open it up again to the rest of the floor. And for those of you who are working on your Explore the Universe. And then when it's all done, you can say, hey, look at that, guys, and stand and review it. All right, is Alan online? Just want to make sure. Oh, there's Alan. All right, good evening, Alan. So tonight's speaker will be talking to us about astrophotography. I'm going to just turn it over to him right away. It is Alan Dyer. And as I understand that when he was a little bit younger, he was actually a member of the Winnipeg Center. Please welcome Alan Dyer.
Yeah, back in the 1970s, oh my gosh, I was a member of the Winnipeg Center. It's my first RASC Center that I joined. Went on to Evanston and now Calgary. And back in those days, I was one of the young whippersnappers for Young Turks, along with Stan and Bill Crosby and Don Ladiak, Hans Stater and others. And I actually helped introduce Roy and Phyllis Belfield, who the older members will remember, to the center as well in the 70s. And of course, they became very active in the club, especially through the eclipse year in 1979. And my father was a carpenter by trade, cabinet maker by trade, and Roy enlisted my father to built his own personal observatory out in Windsor Park, and then the Glen Lee Observatory, the dome, which has since been replaced, and as it should, with a more modern dome. But my dad was involved with the original construction of the Glen Lee way back when, in the late 70s, I guess it was. Well, my presentation tonight, and I'm going to introduce myself in a bit, because the main talk is pre-recorded tonight. I kind of like doing that rather than trying to do a live talk. My internet connection here in rural Alberta, where I'm coming to you from, is not always great. And so just for reliability, I pre-recorded the talk, and it's sitting on your computer there in the room, and Judy will be playing that. And we tested it. It's supposedly it all works in rehearsal. And so that'll be the main talk about getting into astrophotography, step by step. What I recommend for how to get into astrophotography. And so that's what the talk is tonight for beginners just wanting to know how to take pictures of the night sky. So I'm going to disappear. They're going to start the video here on my cue, and then I'll disappear off the live screen. I'll be on tape, as it were, and I'll come back at the end for Q&A as well at the end. So, and I'm watching the chat here as well. But it is a clear night tonight, so I kind of warned the folks there that during my talk, I may not watch my talk, I may disappear and get a camera going to shoot some shots of the comet tonight. So I may disappear off camera, but I'll be back at the end for some Q&A. So guys, if you're ready at your end, you can cue up the video and bring on my video talk, and we'll get it underway about getting into astrophotography. Step-by-step guide. It's a hugely popular area of amateur astronomy these days, and the equipment is better than ever, so it's very tempting to leap right in, because perhaps what you want to capture in terms of nightscape images, Milky Way over a scenic landscape, is something like this, perhaps. But the reality is what you actually capture is this, a little disappointing. And it's not what you wanted to emulate in terms of the images you see on the internet. Or in deep sky photography, what you might want to capture is just beautiful images of famous deep sky objects like the Pleiades star cluster. But the reality is what you actually capture is this very fuzzy view with the Pleiades and cloud. Or perhaps this, where the stars all appear double, something went wrong mechanically there. Or this, everything was out of focus. Or this, the stars had just trailed mysteriously. These are the kinds of challenges that face you, particularly with the more complex form of deep sky astrophotography. Well, what's the solution, of course, to solving all these problems and headaches? It's, of course, buy more gear. We're so tempted by all kinds of telescopes and cameras and filters and mounts. The selection today and the quality today of this gear is better than ever before. It's all very tempting. But I would suggest no. Learn to use the gear you have first. And take it one step at a time. Don't leap full scale into, when you're starting out, into the deep end of deep sky imaging. It is the most complex form of astrophotography, the most expensive to get into. You can spend a lot of money and get a lot of disappointing results. Learn the basics first. Start simple. Learn the basics of operating your camera. So that's the theme of tonight's talk, is learning those basics and taking it one step at a time. So the outline tonight for the talk is, first of all, steps to, what are those steps to success? Learning the sky, a very important step. And then step one, in terms of actually using gear and taking pictures, camera on tripod, nightscapes. Then we'll get into buying better gear. Then we'll advance the technology one notch up, track wide field images. Then we'll put a camera on a telescope, shoot through the telescope, and then the last step is deep sky imaging. In terms of photography, but really the last step, almost the first step, is image processing. I'll have a few words to say about that. So that's the outline tonight. My talk follows the advice that I and my co-author Terence Dickerson provide in our book, The Backyard Astronomer's Guide, two very, very extensive chapters, 17 and 18, on doing astrophotography, and then chapter 18 is doing the image processing itself. So that's kind of, the talk follows the advice and tips that we give in our book. Well, what are those steps to success? Well, start simple with a simple camera on a tripod for just twilight scenes close to home, conjunctions and the moon over a city skyline, or twilight scenes at scenic sites. Again, the sky is not dark, the exposures are shorter, it's easier to see what you're doing, and you can learn the basics. Or advance it a little bit further and get into moonlit scenic nightscapes and get some beautiful results that way. And again, it's a little easier than the next step in terms of the sky is brighter, the exposures are shorter, it's easier to see what you're doing and learn to use your camera. The next step would be into dark sky Milky Way nightscapes. It's now dark, there's no moonlight, no light pollution. You want to capture the Milky Way over a nightscape. It's a little more advanced in terms of the settings and more demanding of your camera and your gear. But then you can start to add some new gear. Add a star tracker for nightscapes, one that will allow your camera to follow the stars. We'll talk about that. You can do beautiful nightscapes that way, or just portraits of constellations or sections of the Milky Way. It's a very powerful form of astrophotography. Before you even get to putting a camera on a telescope, when you do get around to shooting through a telescope, try simple moon shots first. Get into deep sky imaging later and with caution, as I'll outline a little later on. And then do so with the right gear to maximize your chances. If you want to start to spend hundreds, if not thousands of dollars, make sure you're getting the right gear. And I'll talk about some recommendations. And then learn, as you go along, learn to process these images as well. That's key. And last, but actually first, learn the sky. Learn your way around the sky. So that's really almost the first step to success. And really, if you ask any advanced astrophotographer, experienced astrophotography, I bet they're going to agree that the number one piece of advice they could provide, or the thing that they should have done themselves to start off with, is to spend time learning the sky. Just out there with a star chart, books, My co-author, Terrence Dickinson, has this wonderful book out called Night Watch with great star maps in it. That's what I'm using here in the photograph. There's many other monthly guides to the night sky, these simple planispheres that can just learn where constellations are. I find so many people want to leap into shooting the Orion Nebula, and they have no idea where the constellation Orion is in the sky. Other powerful tools are software that you can get for your desktop computers, Galarium.org, free software. All these programs allow you to set up your time and your location to preview the sky that night or whatever into the future. And again, I'm always surprised how many people start to get into amateur astrophotography or astronomy and aren't even aware of these kinds of programs to help them learn what's up in the sky. Or outside at night, you can get the apps for your phones and tablets. I like Sky Safari, that you can then actually move around and it shows you what you're looking at and what's up in the sky above you that particular night. So use those to get familiar with what's up in the sky, just naked eye, where the brightest stars and constellations are. But then get out your binoculars, any pair will do, and use binoculars to find some of the targets you want to shoot that you've heard about, like the Orion Nebula, the Andromeda Galaxy. You can see them with your naked eye, but binoculars show them very well. And again, you can use Star Treks like in Night Watch, the book Night Watch, to help you find some of these objects. And so do that. Spend some time just finding stuff. Learn the sky. Through a year, learn what's up. Learn to identify the brightest stars and constellations. Get familiar with where the moon is at different phases. Get to know where the planets are right now. Learn where the Milky Way is in the different seasons. And find a few of those best-known deep sky objects with just binoculars. Don't depend on computers to find it all for you. People think they'll just spend the money. They don't have to spend any time, just spend the money. No, don't spend money. At first, spend some time learning the sky. Then, start simple. And so step one with actually starting to take pictures is just start with the gear that you may already have. Camera on a tripod. What you need for this kind of photography, a red LED headlamp, you might get that at your local hardware store, a DSLR, or what I call a DSLM, a mirrorless camera, a sturdy but lightweight tripod on a solid ball head, an extra battery perhaps, because long exposures can drain your battery, especially in cold nights, a remote release to fire the shutter, you might not have that. And then start with the lenses you have, but for nightscape photography, 14 millimeter to 24 millimeter is the most popular focal length for most of these kinds of scenes. But first of all, just start with the equipment you have. You may already have some of this equipment, the camera and the lens that you have. Now, I am assuming here the use of an interchangeable lens camera. Yeah, you can get some nice shots these days with phone cameras. They're very advanced. But for the most part, to really graduate to more serious astrophotography, I'm talking about interchangeable lens camera. It could be a DSLR, a digital single lens reflex, or a mirrorless camera like I showed on the right. And that allows you to change the lenses and put in wide-angle lenses, particularly useful for nightscapes, and change the lenses up, or as we'll see, put the camera body itself on your telescope. So that's the best kind of camera to start to use for astrophotography. And using it to do some simple nightscapes, you learn how to operate your camera in the dark, how to focus at night. We'll talk about that. Frame and compose at night. Judge exposures and set your camera. And plan shoots for the best sky position and lighting opportunities. That's a lot to learn with just your simple camera that you already have on the tripod that you might already have. Well, the number one question beginners want to know, however, is, well, I've got all the gear, what's the best exposure? And it is important to get the exposure correct. And this is where you learn the basics of operating a camera manually, because you have 3 ways to affect the exposure. And these, for astrophotography, all have to be set manually. If you've not done astrophotography before, you're used to just using your camera automatic, and you can do a great job by day, but typically not by night. You can vary the shutter speed, the shutter duration. For nighttime shots, it's typically 10 to 40 seconds. You can change the lens aperture, how wide open the lens is. And for this kind of photography, it's typically f2 to f4 is where we set the aperture. Or you can change the camera ISO speed. It's kind of how much the sensor, the electronics in the camera, amplifies the signal coming from the sensor. And typically we're at a pretty high ISO, 800 to 6400 for nighttime shots. Those two settings, shutter and lens aperture, are the only two ways we have of actually increasing the amount of signal coming in to the sensor, the amount of light that we can capture. This setting, the ISO speed, just boosts the brightness of the signal that we collect. So it's important, but only duration and lens aperture allow you to actually increase the signal, which is all important at night. The shutter duration is typically 10 to 40 seconds, can be longer with wider lenses, but there is this 500 rule. It's a very, very rough rule of thumb that the maximum exposure you can use with a camera on a tripod is about 500 divided by the lens focal length in millimeter. And so typically your limit is 30 odd seconds or so before the stars begin to trail. And so that limits our shutter speed for camera on tripod shots. The lens aperture, often f2.8, is the best compromise. If you go wider, if you have a wider lens, it might be useful, but often these aberrations at the corners of the lenses become much more apparent. And so it depends on your tolerance for those aberrations. Stop the lens down, and the lens gets sharper, and you just get a little bit better, but the exposures have to be longer. So that's always the compromise. All these settings involve compromise. With ISO speed, for example, as you increase the ISO speed, the noise goes up. The image looks grittier and grainier. So it's nice to use a high ISO speed to get a nice bright image, but it starts to look noisier. So there's always a compromise, always a sweet spot. What's the best ISO, aperture, and shutter speed? For moonlit scenes, it's typically 5 to 20 seconds. At 2.8, at 5.6, we've got more light to work with at night with the moon up, and ISO 400 to 1600, so not terribly high. And you get some beautiful moonlit scenes still with lots of stars in a nice blue moonlit sky. The auroras, and I'm lucky to live here in southern Alberta where we can get auroras fairly often, right from my backyard, sometimes filling the sky. No matter where you are, auroras, see them 5 to 20 seconds at 2.8 to f4, ISO 800 to 3200. It really depends on how bright the aurora is and how bright the sky is on that particular night as well. But those are ballpark figures. For auroras, gosh, the wider the lens, the better almost in many cases. Sometimes I shoot with like a fisheye lens for a display that goes over the whole sky. But typically you need a wide-angle lens for the aurora or the northern lights display. Now, Milky Way nightscapes, what most people really want to capture for nightscapes, is the beautiful core of the galaxy, perhaps over a scenic landscape. It's dark. There's no moon up. There's no light pollution. You need a site that's dark. 30 to 40 seconds. That's pushing the amount of exposure time you can use before the stars trail. F2 to f2.8. You need a fast lens. That's the key here. And ISO 1600 to 6400, maybe even higher in some cases. And so you're really pushing the limits of your exposure time. You need a fast lens, and you're pushing the limits of what your camera can do as well at the high ISO settings. You can do star trails where if you can get one nicely well-exposed image, you can shoot lots of them, 50 to 300 at a 1-second interval, and then use a free software like StarStack to stack the images. A key thing is to use an intervalometer either built into your camera, as I show on the left, or an external intervalometer to keep firing the shutter automatically. As soon as one exposure finishes, the shutter fires for the next one. And you take a few dozen, if not a few hundred of those images to stack together to make star trails. So that's another neat form of nightscape photography. So what's the best exposure? There is no one single exposure. The best combination will depend upon the scene, what it is you're shooting. Do you have foreground objects that need to be in focus, in which case you might need to stop the lens down for more depth of field. Your lens's focal length, it will vary. A wider lens, you can use a longer shutter speed than a longer focal length lens. Your lens's aberration performance, how good is your lens? Can you use it wide open at 2.8 or f2? Your camera's noise performance, how well does it work at 1600 or 3200? And the only way to learn is to shoot. To shoot and to shoot again. That's the way to learn. You can watch as many videos like this one as you want, but the only way is to get out there and learn from your mistakes, look at the results from your equipment and see what works best. Well, other camera settings,
By far, the most important setting for any kind of astrophotography with the DSLR or mirrorless camera is always shoot raw. It records the full 14-bit data from the camera. You get greater dynamic range, best highlighted shadow recovery, full control over the white balance. People say, what's the white balance? What should I use? Doesn't matter if you shoot raw. You can change it at any time. And allows you full control of noise reduction, much better noise reduction than you might be able to apply later on. And so always shoot raw, the largest uncompressed raw format that your camera allows. Other camera settings, well, as I say, people do ask about white balance. I tend to, if you put it on automatic, it'll work, but I tend to use it on a fixed Kelvin 5200 daylight setting. I set picture styles, in this particular case a Canon camera, other cameras call it something different, to a neutral setting. It's that affects what your preview of the image looks like when you play it back, because you're looking at the raw image, but a JPEG that the camera has captured as well. Put it to neutral, that will better resemble what the raw image will actually look like. For color space, I set it to Adobe RGB, but in fact, I think that only affects JPEGs. And for mirrorless cameras, I tend to always put the shutter on mechanical rather than electronic. You get a better dynamic range with the camera on a mechanical shutter setting with a mirrorless camera. The key, however, to getting well-exposed great images is called exposed to the right, ETTR. Shoot long enough to show details in the shadows and foreground, and use the histogram as your guide. You don't want to underexpose and get very dark shadows, very dark foregrounds, as here. On the left is a correctly exposed image of the histogram shifted over to the right. On the right is an underexposed image. The histogram is slammed to the left. Histogram comes up on your camera. There's ways of showing it on your camera, either when you're taking a picture or when you play it back, to check on the exposure of your camera. You want to avoid what it looks like on the right. Again, the histogram is a plot of the number of pixels versus the brightness. And so more dark pixels, more underexposed pictures, that histogram will be a big mountain peaking to the left. If it's more properly exposed, it'll be distributed more across the whole range of brightness here. But inevitably at night, we are dealing with very dark scenes, so it's hard to get a histogram where it's maybe exposed all the way over to the right. You don't want to clip it too far to the right and overexpose right sections. But so don't slam the histogram either to the left or to the right. Get it as well distributed as possible, because it makes the biggest difference to the quality of the image. It's better to shoot at higher ISOs and longer exposures. Don't shoot at short exposures and then think you're just going to fix it later in processing. Because what that can do is, what I'll show you here in a sec, is it increases the noise and the flaws. Give the sensor signal when shooting. Here's two images, one on the left properly exposed, one on the right underexposed by 2 stops. That's what came out of the camera. And then here on the right, I've taken that same underexposed images and brought it up brighter in processing. Increase the exposure value in processing. Now on the right, it looks the same brightness. The histograms look the same, but which one's noisier? The one on the right is much noisier. And so if you try to fix things later in processing with an underexposed image, you can just make things look much worse, introduce more noise and artifacts. And that's the #1 issue I see with people's pictures of all kinds of astrophotography, not just nightscapes, also deep sky. They don't shoot long enough, and the exposures are not long enough and not well exposed enough. And so you're just introducing more problems. So exposed to the right. The other issue, if you think exposure settings are a challenge, this is the #1 surprise beginners discover, is focusing. Again, by day you're so used to just automatic and boy, it's done, and the camera does it for you. At night you've got to manually focus for the most part. And this is the biggest surprise, is the difficulty of seeing anything to focus on. The best way, really, to focus with a DSLR or a mirrorless camera is to use live view with a DSLR. With a mirrorless camera, it's always in live view. And then you zoom in with a little plus button there cameras might have, or DSLRs might have the LV button that you press to turn it into live view, flips the mirror up, and now you find a bright star or planet in the sky and zoom in on it with the plus button. to make that star kind of as big as possible in the live view screen, and then manually focus the lens to get that star as sharp as possible. And then don't touch the lens after that. Take it off autofocus, take the camera off autofocus, manually focus with the live view. And that's really the best way to focus at night. It can be a challenge, just finding an image, just finding a star to focus on. Turn on exposure simulation. That's an option that's present in most of the menus. That can brighten the image and make it easier to see. On the left is a typical view through a DSLR camera, a good DSLR camera, a Canon 6D. And you can see there are stars, but on the right is what a mirrorless camera can do. They're much better for showing a live view scene that's really bright. In fact, even showing the Milky Way live. Often it takes turning the DSLR or DSLM mirrorless cameras into a movie mode and really cranking up the ISO to 64,000 or 120,000, and you can see and focus a lot better with today's mirrorless cameras than with DSLRs. Or another option, certainly for framing, and you might want to do this anyway, is just put the camera onto a very high ISO and just take a 2 or 3 second exposure, just a test shot, just to judge the focus and the framing, and to kind of iterate, take lots of different shots to make sure it's framed the way that you want. And then don't forget to take the ISO down to a lower level that you actually want to shoot at. But focusing and framing can be a real challenge at night. The best practices at night are to shoot at a lower ISO, longer exposures or a wider aperture, and use those best ETTR exposures. And shoot multiple images for later stacking as well. And sometimes it takes different exposures for the ground, a longer one for the ground to reveal detail on the ground, and a shorter exposure for the sky. It's actually the sky that is much brighter typically than the ground and a lot of nightscape shots, and then you blend them later. And I suggest shooting with what's called long exposure noise reduction, LENR, on when possible. It's not always possible. You want to take shots in rapid succession, like for a time lapse or a star trail. But I find many, even highly skilled professional photographers, astrophotographers, or even other landscape photographers don't understand what LENR does. They figure, well, no, I'm going to do noise reduction later in post-production, in processing. Yes, you can. Not noise reduction that will produce the kind of noise LENR eliminates, which is thermal noise generated by your camera sensor. It's hard to get rid of later in post-production because it leaves all kinds of hot pixels through the dark areas of an image, or colored pixels. There's things called dark frames that you can take later and subtract later, but I found with this kind of, any kind of astrophotography, they don't do as good a job with the DSLR or mirrorless camera. They can also introduce artifacts like black holes. And the only way to truly, cleanly eliminate this thermal noise is to turn on LENR, and the camera takes the dark frames and tracks it and gives you the cleanest possible image, free of those thermal noise, hot pixel artifacts. They're hard to get rid of later in processing without maybe blurring or ruining detail of the image. So that's long exposure noise reduction, particularly on warm summer nights. If the camera's warmer, you'll get that work. So I suggest using LENR when you can. Cold winter nights, maybe not so much of an issue. People ask about filters as if there's some magic bullet filter you can just buy, stick it on, and the pictures will be marvelously great. No, I've not really found that. There's light pollution filters, I've tested them. They can do a nice job to some extent of reducing the sky background and bringing up the contrast a little bit in the Milky Way, but they don't make a huge difference. Deep sky photography, a little bit different, but for nightscape photography, filters, don't expect them to make a tremendous difference. The best way to get great Milky Way shots is to go to dark sky sites. And for planning your shots, I like to use planetarium software like Sky Safari or Stellarium. For planning a frame, you can set them up with fields of view of your lenses so you can see what area of the sky your lens and camera combination will capture. To plan what's the best lens to use. But for nightscape photography, you want to know what it's going to be like over a particular scene or landscape. So we have specialized apps for that. I like to use the photographer's ephemeris, TPE is called, where this is the image of that app showing you this particular shot, previewing it from standing at that location. Where is the Milky Way going to be down the lake? The Milky Way is shown by the line of dots there. There's a companion app called TPE 3D that you can switch to, and then it shows you actual topography It shows you the actual Milky Way over the mountain landscape, mountain skyline, to really perfectly simulate the scene that you're going to see from that location. Another app people like to use, I don't use it as much myself, it's called PhotoPills. It has a lot of the same capabilities. So great, that's a lot to learn. And we haven't even started to spend money yet. So let's get into buying better gear. And there's lots and lots to pick from. Better gear than the camera lens that you might have. Well, these days we have two main options for new cameras. It's that a DSLR mirrored camera. It's got a mirror that flips out of the way when it takes a picture, or a mirrorless camera, where the sensor is always seeing and relaying an image to a live view image in the electronic viewfinder or to the rear LCD screen as well. Those are your two main choices. Really, for a new camera now, it's almost mirrorless. Nobody's making brand new, introducing new DSLR cameras now, except for Pentax. They're staunchly staying with DSLRs. But no one's, Canon, Nikon, Sony's discontinued DSLRs. Canon and Nikon still sell DSLRs, but they're not introducing any new models. They won't. No one expects them to now. It's all the focus is on mirrorless cameras. So if you want the latest camera, even the latest DSLR made was probably made 2 or 3 years ago in terms of how old it is. So eventually it's going to be discontinued and not supported any longer. The future with cameras is the mirrorless cameras, and for astrophotography, they can make a big difference. In terms of, as I showed you earlier on, give you a much brighter, better live view image to make it easier to focus and frame images as well. So that's one big advantage with a mirrorless camera. Also, mirrorless cameras have sensors that are called ISO invariant. They're much more tolerant of underexposure and bringing out the details in the dark shadows of the nightscapes. Whereas a lot of the DSLRs, particularly from Canon, are not ISO invariant. So, as I show in the center here, they really suffer from noise and artifacts. Even if you use that exposed to the right methodology, you can still get a lot of ugly-looking artifacts in the shadows with the DSLR cameras. The new Canon mirrorless cameras all have ISO invariant sensors, give you much cleaner results. Particularly for this kind of landscape photography, you do see the advantage in image quality. Then you have a choice of full frame versus crop frame. Full frame means the sensor is the size of all 35mm film, 36 by 24mm. Crop frame, and all the manufacturers have crop frame mirrorless cameras now as well, 23 by 15mm or so. As a rule, full-frame sensors are generally going to be less noisy and so are better for astronomy work. So if you can, go for a full-frame camera. If you're really on a tight budget, go for a used full-frame camera, perhaps a DSLR, Canon 6D or something like that, or Nikon D750. Go for a used full-frame DSLR. But getting into a brand new crop frame camera, they'll work, but a full-frame camera on a mirrorless model will be better for astrophotography. However, the biggest difference you can make to your image quality with the camera you might already have is to buy a better lens. The kit zoom lenses are great for a lot of images that you can start off with, but a better, faster lens, a fast wide-angle lens, f2 to f2.8, and a 10 to 24mm focal length. 14 to 20 is sort of the most popular for nightscape photography. There's even zoom lenses that cover that range as well. So buying a better, faster wide-angle lens is going to make the biggest difference, and you can use them later on for deep sky Milky Way images as well. You don't have to spend a ton of money because there's manual lenses available from companies like Rokinon, Samyang, that are very good, that are just manual focus lenses, which we're doing anyway, and have excellent speed. And just make sure you buy the lens that's going to fit your particular camera. And there's lenses that are nice and tempting, but they only work on crop frame cameras, in particular, a certain brand of crop frame camera. So make sure you get the right lens for your particular camera body, or what your future camera might be later on as well. But there's other models from brands like Laowa, TT Artisan, Irix, the same art lenses, autofocus, but they're also excellent. generally a little cheaper than the actual original lenses from Canon or Nikon or Sony as well. So there's lots to choose from on the market today. And zoom lenses, the received wisdom used to be that zoom lenses were not as good as the fixed focal length prime lenses. That's really changed. That's one other big advantage to going with a mirrorless camera, is the lenses, which will fit only on those mirrorless cameras, are much better than the lenses of even a few years ago for DSLRs. And particularly the zoom lenses from Nikon, Canon, and Sony have really improved a lot. And they're as good, if not better, than a lot of the older prime lenses. I shoot almost nothing but zoom lenses for a lot of my astrophotography now. I wouldn't have done that a few years ago. So the lenses have improved for mirrorless cameras. Tremendous. That's a lot to consider if we haven't even gotten past step one, camera on a tripod. Now, maybe you've got the right lens or the right camera or whatever. Now we can start to get some specialized gear for astrophotography by getting a tracker, a sky tracker. It can follow the stars, and so it allows for longer exposures with no star jump. We don't have to worry about 5-year rules. We can shoot at a lower ISO speed for less noise. We get more detail in the Milky Way. The drawback is that the ground is going to blur during your exposure, so you have to take a separate exposure of just the ground with the tracker motor off, and then blend into exposures later on. And trackers, as with all equatorial mounts for tracking the sky, need to be polar aligned. I'll talk about that in a second. So it's an extra step that is somewhat daunting for people just starting out in astrophotography. And so trackers can do some marvelous shots. I use this very gear right here, the little Star Adventure Mini, that lens, the Canon RF 15-35 for this shot, and a blend of tracked and untracked exposures. But you can also use them to get into deep sky imaging and just shoot portions of the Milky Way and constellations. Use a telephoto lens to zoom in, as I did here, on parts of the Milky Way. So it really gets you into deep sky imaging quite easily. You still need great dark sky sights to get the best images. The best exposures for using a tracker, typically 1 to 4 minutes. Not really long, but f2 to f4, you can maybe stop the lens down a little bit more, go for a longer shutter speed, and the lower ISO, 400 to 1600 perhaps, something like that, where most cameras will perform quite well and not be too noisy. So trackers make it possible to get some great shots, deep sky shots. This is Cassiopeia, relatively easily once you learn things like polar aligning. You learn how to seek out dark sky sites and polar align them, plan the framing of fields, actually frame and focus on star fields, set exposures for deep sky images, stack and align images in processing later on, a key step. And then contend with a whole manner of other kinds of challenges that I kind of showed you at the beginning as well. So that, you start to learn those techniques, those habits that you'll need for more advanced deep sky imaging later. The key to using a tracker is polar alignment. And this ties into learning the sky. People get a tracker and they want to use it and they have no idea where the North Star is, no idea where Polaris or the Big Dipper is. Learn the sky, learn where the Big Dipper is, the northern hemisphere. It's always in our sky. The pointer stars point up to the Little Dipper and to Polaris, the North Star, as I showed there. The North Celestial Pole is very close to Polaris. Polaris is always in the same spot in the sky at your latitude. It doesn't move through the night or during the year. Once you found it, that's due north. And so you do this a few times, it becomes very easy to do. So you want to set up the rotation axis of the tracker using this little polar alignment scope so it rotates around the North Celestial Pole. And it's good to be accurate here because it's easy enough to do. You set up your angle to equal your latitude, and you use the adjustments on the base of the mount, at the altitude and azimuth adjustments to sight Polaris and put it where the app. Most of these trackers have a companion app for your phone, which knows your time and location and tells you where Polaris should be on the reticle. And you just use those adjustments on the base of the mount to put Polaris where it tells you to put Polaris. And you're done. With a little experience, and it only takes it 2 or 3 times, you're doing this in 15 or 30 seconds. But people do struggle with this because they haven't taken the time to even learn the sky, even learn where the North Star is at their home latitude. So it's easy to do, and you learn to do it pretty quickly. Then learning to seek out clear dark skies. I like the app Astrospheric, astrospheric.com for a weather app to find where clear skies are likely to be. Also dark skies. This is a light pollution map of my area. The grayer, the darker it is, the darker the skies, to get into the better Milky Way shots, get away from the city light pollution. Now for tracker choices, these are some models I've used and can recommend. Star Adventure Mini, I like it for a lot for nightscape images, nice and portable. For a little heavier, but able to take a little heavier mount, a heavier telescope and camera, Star Adventure 2i, and then the Ioptron Sky Guider Pro. I've used that a lot, and it's another excellent tracker as well. So those are three that I've used and can recommend for trackers. So you're looking at, your $500 range or so to get into a tracker like that, in addition to your cameras. They can be used with lenses up to 135 millimeter, maybe longer, but longer telephotos and small telescopes like I show on the right, people use them with these telescopes, but it can be a challenge. They're harder to aim, and the tracking of these little trackers is good, but it starts to show the inaccuracies that they have as you get into longer focal lengths. It becomes frustrating. For something like this, in fact, that's what you may end up getting. There's a lot of images that look like that. If you try to push a tracker too much and use it with too long a focal length telephoto or a small telescope. They're great for short telephotos. Because what can go wrong? Well, this, for example, the drive just stops turning, something jammed, something snagged, the battery's died, whatever. Dew or frost gets on the lens. You're fighting with that all the time. The optics aimed up. So you buy one of these dew heaters and you put that on the lens, and the strap falls in front of the lens and ruins the picture. Or clouds, of course, come in. So lots can go wrong. Welcome to astrophotography, and that's just with civil equipment as well. But you've got to get the patience and write out these kinds of challenges and overcome them and start to get some great results. And you will. You will. Well, step 3, this is what people really want to do, though, is they have a telescope, they have a camera, they want to put them together and start to shoot through the telescope. Well, because that's what you really want to shoot. These great, beautiful, deep sky objects. Okay, but first of all, we have to actually attach the camera. And this is where we need the mirrorless camera, or rather the interchangeable lens camera, to take the lens off. We put on a special camera adapter. You can get that in your local telescope store or whatever online. And with a T-ring made for your particular camera lens mount, Sony, Nikon, Canon, whatever, and then that gives you a nose piece that you then attach into the camera, into the telescope, where it replaces the eyepiece, and the telescope becomes the camera lens. And these kinds of adapters, I say, are available from Telescope, because you have to make sure you get the right one for your telescope and for your particular camera as well. What are the suitable telescopes for putting your camera on and shooting through? Well, refractors, Maxitobs, and Schmidt-Cassegrains are fine. They'll all reach focus generally. Newtonian reflectors, maybe not. And they're great value for buying a first telescope to look through. But often cameras are not going to reach focus with them. They're not designed for photography with many of the entry-level reflector telescopes. So you can't actually rack in far enough to allow the camera to reach focus. Sometimes with the entry-level reflectors, you need to put what's called a Barlow lens between the telescope and the camera, and now it extends the focal plane out further, and now your camera will reach focus. And what are you going to focus on now? What are you going to shoot? Well, by far the best thing to start with is the moon. It's bright, exposures are short, snapshot almost, and the F ratio is whatever your telescope is, maybe multiplied by a factor of 2 if you're using a Barlow, and the ISO speeds can be quite low as well. You don't need to use high ISO. The moon is really quite bright. So it's easy to shoot, even if you don't have any kind of tracking ability on your telescope. Just an old Testament mount telescope will work without any motors, whatever. You get some nice shots of the moon. It's a great way to start. You learn, you're shooting the moon through a telescope, how to operate and aim your telescope. Center and frame targets. You're looking with a lot of magnification, so just getting the image centered is a challenge. focusing your camera when on a telescope. The image is going to be that much dimmer. It's a little more challenging to focus on even the moon. And you contend with all manner of other challenges, wind blowing the telescope around, vibration, things like that as well. So it's not as easy, but you learn how to overcome some of these challenges. Or this is where you can, with the right adapter, and some of the entry-level scopes come with these adapters included, to clamp your phone onto the eyepiece, so it is looking through the eyepiece, and you can get some shots of the moon that way, quite simply, just using your phone camera to shoot through the eyepiece of the telescope. And so that's a fun way to kind of just get into it, and get some things to whet your appetite for shooting the moon. But for the most part, as I say, shooting anything else with any camera through a telescope is a challenge, other than the moon. The planets are very, very small. It takes a lot of magnification. And usually the best images require the special, very special, the movie cameras essentially, to get good shots of the planets. I don't even get into that myself. These sky objects, however, are very dim and bright on the ones like the Orion Nebula. They require lots of exposure time, many seconds and not many minutes long. And a telescope on a solid mount, that can track the sky. So you do need the motor drive to allow you to follow the object during the time that you're exposing. So now we're into step 4. Finally, we get to what people want to start with, but now we're into step 4, deep sky imaging. What you need to learn is everything up to now, plus operating a go-to mount, one that can find these objects for you, knowing what to shoot and when best to shoot. As I say, people sometimes, oh, I want to shoot the Andromeda Galaxy, and it's April. It's not up. Or the Orion Nebula, and it's July. It's not up. Finding and framing faint targets and connecting all these various components, you get into a quite complex array. It's quite complex putting it all together, this mix and match of components to make it all work. Operating things like auto guiders, very specialized pieces of gear, and control software with tablets or computers. It gets really, you're throwing yourself up a notch quite a bit. Here's a good method to start, however, for those who really want to get some deep sky objects through their telescope. With any telescope that is aligned in tracking the sky, even an alt-azimuth go-to telescope like I show here, as long as it's tracking the sky. With the camera, try and focus just as you would, got some experience with you shooting the moon, and focus properly. Aim at a bright, deep sky object, like the Orion Nebula or the Andromeda Galaxy, and just take lots of 30-second exposures at high ISO, 3200, 6400, 12,800, just really high ISO. Just take lots of them. You're not guiding, but you are tracking, and you just take lots. Some will be spoiled, but take the best of them, and you can stack them later in processing and get a pretty decent result. The stacking smooths out the noise, it'll align itself, and you can start to get some nice results of some of the brighter deep sky objects. Just to whet your appetite, just to get started. But however, it's not going to be the best quality, but it allows you to kind of get used to doing deep sky photography. If you really want to get serious, what you need to buy is equipment like this. And this is what I would suggest. People buy a huge monster telescope for deep sky imaging and expecting they're going to really get killer shots. Actually, the best shots to start off with, the best kind of gear to start off with deep sky imaging is a small telescope, a small refractor like this, 60 to 80 millimeter apochromatic refractor on a solid German equatorial mount, so one that can be polar aligned, can track the sky, not a melt-azimuth mount. Got 2-axis motors, one for tracking the sky, one for moving it north-south, so you can auto-guide, an auto-guider, a separate little camera, and a scope for auto-guiding and keeping stars perfectly pinpoint, and this associated control software. A fuel flattener lens often is needed with these telescopes. The telescopes come with that as an optional accessory. And you can expect for even a basic entry-level setup like this to spend $2,000 to $3,000 without the camera. It's just using the camera you're already have. And so that's the kind of setup that I would recommend for those that really want to get into deep sky imaging. There's kind of levels. You can use just your basic sky tracker, for example, or take it up a notch with a We have today these compact go-to mounts. They're well under $1,000, but they're fully go-to mounts, but they're lightweight, portable, easy to carry around, or step it up a notch with a larger German equatorial mount as well. But still, you're looking at $1,000, $1,500 for a mount like that. Basic sky tracker, you can use it with the telephoto lenses, as I said. On these compact go-to mounts, use with a very small 50 to 60 millimeter Apple refractor. They'll handle those quite nicely. But if you want to get into a bigger telescope, like an 80 to 100 millimeter scope, you need perhaps a little bigger equatorial mount. Well, either way, you're looking at $2,000 to $3,000 to get fully equipped, as we showed here more on the right. So those are your options for getting started as far as equipment goes. But what you need to have is clear, preferably dark skies. The darker the better. And you need free nights. You need nights when you can go out to those dark skies and lots of time. You need patience as well, because you're overcoming all these challenges. By all means, start from your backyard. Take some shots from your backyard, suburban backyard. See what you can get. Learn to use the equipment from your backyard. And so you're not trying to learn all this stuff outside, out in the dark, at a dark sky site that you may not get back to for several weeks. So it's the willingness to spend lots of time and money, often for only a few images in return, but they can be very rewarding images when it all goes well. But those are the kinds of steps that I would suggest allows you to get good results right away by starting slowly, learning a lot of the basics, and then getting to deep sky photography. The last step is, of course, processing. It's so important because it makes or breaks an image. What comes out of the camera often needs a lot of work to really make it look great. Image processing. What it can do is it can turn this into this, or turns this piggyback shot, tracker shot into this, or this prime focus shot of the Pleiades into this. And I'm not going to get into how to do image processing here. That's a whole big tutorial into itself, or several as well. But it is very important, and it's important to start to learn how to do that with your simple shots first, and then work your way up to the more complex deep sky images that require stacking and all kinds of specialized processing to really bring out, extract the maximum detail in those deep sky objects. So that's my tour of getting started. The summary is, learn the sky. Start simple with the gear you have. Buy gear when you really know what you need. Start deep sky imaging with a simple tracker first. Don't dive into deep sky imaging right away through a telescope. And then when you're ready to start to do that, buy the right gear. It may not be the camera or the telescope that you own now. You may need a specialized rig for deep sky imaging. And learn to process images as you go. So that's my tour of getting and my advice for getting started in deep sky or into astrophotography in general, my step-by-step guide. My website is amazingsky.com. And again, this advice follows the tips that we have in our book, The Backyard Astronomer's Guide. It's 4th edition, and it's all about a book. The site that tells you all about the book is backyardastronomy.com. So thank you very much for inviting me to speak and for attending my talk tonight. And I guess at this point, we're free to take some questions. Thank you.
Hopefully we're back. Hopefully we're back live. Speaking there, I can hear you fine. I'm not going to hear the audience. If there's questions from the audience, you'll just have to relay them to me. I don't see any questions in the chat. So if you've got some questions from the audience, be happy to take them.
I have questions.
What was his first camera he ever bought?
first camera that, well, now you already got to date me now, because it's Nikon film cameras, a Nikon F, and then an F2, back in the 70s, I guess, and I still have one of them. And then in the last stages of my use of film, I was shooting with 6x7 medium format film with a Pentax 6x7 cameras. One I gave away to a friend in Australia, but another one I still have. But I've got rolls of film in the fridge for the last 20 years that are still in the fridge. But the first DSLR camera I bought was the Canon, what do they call it, 300D. It was the first kind of affordable DSLR. They were several $1,000s in the early days. But this was 2004, 2005. And I bought this 300D camera with whatever lens, because, it could take whatever lens I would have had at the time. I'm not sure what I was using at the time. But I started equipping the camera with Canon lenses, and in fact, I'm just selling off all the DSLR lenses and getting the RF lenses. But I remember I took that camera to the Saskatchewan Star Party and took some nightscape shots, and by starlight, I could see the green grass in the image, which was impossible with film. And then I just boxed up all the film cameras and sold them to the used camera store downtown Calgary, and that was it. Film was over. And I've not looked back since. I'm still buying new cameras. As we speak, there's a Canon R5 and the 28 to 70 millimeter lens outside shooting the comet in a wide-end field with Taurus and the comet sitting right above Mars tonight. So now I can see some people. Hey.
Any other questions?
I'm curious about how you would image deep sky contact objects like a ring nebula or dumbbell nebula.
I have to relay the question. I can just barely hear somebody.
Well, like the ring nebula, because they're smaller. Like I'm not really interested in wide field, I'm interested in narrow field.
He's interested in narrow views?
Field.
Sorry, narrow field. And what your recommendation?
He's answering it.
How do you define narrow or wide field?
Ring
Wide
nebula,
field.
ring nebula, dumbbell.
Okay, all right. Let me answer the question to see if we get over the audio feedback. If you want to shoot real big close-ups of small deep sky objects, like planetary nebulas, ring nebula would be a good example, you've got to shoot with a lot of focal length, 1,000 millimeters, 2,000 millimeters. That's the most difficult type of photography to do, because your polar alignment has to be spot on, your guiding has to be spot on, has to be no wind if you've got a big scope. Even the seeing conditions have to be pretty good, otherwise your image could be blurry. It's really tough. That's why I say if you're starting, don't do that. You're just setting yourself up for failure. Shoot with a wider field, and by wide field we're talking about 3 or 4 or 5 or 6 degrees, a focal length of only 300 to 600 millimeters with a small Apple refractor is enough to shoot lots. It's what I shoot mostly. And I haven't run out of stuff to shoot with it yet, so that's what I shoot with. It's so much easier to set up. I see people setting up these great big green scope rigs and they're going to get their killer shot, and 3 hours later they're still setting it up. And it's clouded up, and then they take it all over and go. Don't do it. If you've got a permanent observatory, it's a little different story. Then you can be more ambitious, especially in a dark sky. You can be more ambitious and get a dream set up and really go to town. In a portable setup, even here, I'm in the country. This is my view from my backyard, not live now. And I don't have an observatory, and I set up here, you know, I just did a few minutes ago. And so I like it to be easy to set up and portable. It's just so much easier. Then I'm getting old.
So did the check, there's a question on the chat.
Yeah.
Is there a safe way to transport your telescope and camera gear overseas?
Good question. You just got to pack it really well. More than you might think. I've had a telescope that only came back from Australia last time I was there in 2017, because I knew I was going to be back for a while, so I brought it back to me, but it lived in Australia for many years because I have relatives there. Its focuser got kind of bent on the previous trip down, whatever. You think it's packed really well, but boy, the pressure in the suitcase can really bend something, a tripod or whatever, so you got to pack stuff really well. If you're putting it in a check bag, which big stuff you almost have to. But if it's smaller stuff and delicate stuff, and that's where like a little small optical refractor, you can take on the carry-on, perhaps. And delicate stuff, the cameras I always typically would take on a carry-on, and a lens or two. I'm going to Churchill next week, not overseas, but still flying 2 flights to go up to Churchill. And all the cameras, apart from 1 or 2 lenses, which it'll be in a check bag. The camera and the lenses will be in a carry-on bag, but the tripod's got to go with the check bag. But you've got to pack it well, because you'd be surprised how much can get twisted and bent, and all it takes is a broken tripod and you're out of business.
So, why do you like digital full-frame cameras over, say, dedicated astrophotography cameras?
I think I've heard that. I use nothing but, well, previously DSLRs, but now mirrorless cameras, because I just like the convenience of them. They're easy to use. I don't like computers at the telescope. It's just more things to go wrong, and to set up, and to power, and cables, and software to run. And you saw the difficulty you had tonight with your Windows computer getting the damn sound going, at least for us here at this end. You know, imagine what it's like at minus 20 degrees with your Windows computer and something's going wrong. I just forget it. It's just too complex. And so all the dedicated cooled CMOS cameras, of course, require a computer to run and to store the images. But you can get, and I showed in a couple of pictures, the little ASI Air control box. I have 2 of those, and they're great. They're great. And now you can just run the computer off run the computer off your tablet. So that's nice. That's not bad. But I just like to keep things simple. And I've yet to see a good comparison of a good DSLR camera. A good DSLR, not some 15-year-old T3i or something. A good DSLR or mirrorless camera compared to a modern CMOS camera, and to see that it's so much better with the cool CMOS camera. Yeah, you get the monochrome cameras and all that kind of stuff, and if you want to get into that, that's really complex. Filters and all that. One filter can cost you as much as entry-level mounts or whatever. And so I just shoot with nothing but the mirrorless cameras now, and the results to me look really great. Now, I often shoot with modified cameras that have the filter modified to pick up more of the red sensitive nebulas and things like that, to pick up more of the nebulosity. I was shooting with that modified Canon R 2 nights ago out of Dinosaur Park, getting all the red nebulas along the Milky Way. So absolutely, that's nice if you want to go after those kind of deep sky objects. But I am yet to get into the cool CMOS cameras as well. It's just too much to fuss around with out there at night in the cold and dark. But people do. I wander the star party fields now. see nothing but the red ZWO cameras out there. It's almost become de facto. It's what you buy to start off with. Go ahead, and you might ramp up, and you might get Toyota to use them and get great results. But start with the camera you have now, DSLR and mirrorless camera, and see what you can get with that. There's a lot you can do with it, and because you still got to learn how to focus. You got to learn all those steps. I had 40 minutes of steps you got to learn before you even got to that stage of using one of those cameras. And as I said right at the beginning, the answer is not buying more gear. Using the gear you have, learning how to use the gear you have. We all want excuses to steady.
There's a question on the chat, maybe not simple. Where has been your best dark sky to set up?
The very best dark skies have been in Australia, where I was hoping to go next month in March, but I canceled that trip for various reasons. Cunnaverra brand, you don't have to go way into Ayers Rock or whatever, Uluru, fabulous dark skies. And then Chile, Las Campanas, Terrence Dickinson, bless his heart, he invited me along on a trip in what was it? 1992, I think, or 93. We were shooting film, gosh. We went to Las Campanas. We got 9 nights on Las Campanas. And then I've been back to Chile a couple of times. Again, trips that Terry was organizing with Sky News back in 2010 and 2011 near San Pedro de Atacama. But that's the southern sky as well. You can't get that here. But here in North America, the southwest U.S., I like to go to a spot near Rodeo and what is it, in southwest Arizona, southeast Arizona, southwest New Mexico. In there, the dark Arizona Sky Village area, it's a nice spot. But anywhere in the desert southwest is great. But here in Canada, Cypress Hills is fabulous. I know some of you have been out there, but you've got great sites in southern Manitoba as well. Just get away from the lights and you have some great sites. And then, of course, we have the advantage. You might think at a disadvantage, but people spend thousands of dollars to see what we can see from our backyards. The Aurora. So you don't necessarily need fabulous dark skies to have a wonderful sky show.
Any more?
All right, well, that's it.
Thank you very much. It was a great presentation. So again, thank you. So that concludes our evening. Thank you to our speaker tonight. And as I said, that concludes our meeting. For those who are interested, some will be gathering over